This is Saxon Advanced Math 64.b, polar form of a complex number. Now, in order for us to understand this, we've got to remember a couple of things and pull back our memory on what we would do when we're converting from regular rectangular format into polar format with a normal or a regular number. And so we're going to start with that. The rectangular form of 2 root 3i plus 2j, I hat and j hat. And if I did this, that's the x and the y coordinates, right? And so if I did this in rectangular form, I would say this point right here, and I'm gonna emphasize this little guy right there. That little point right there is the point that is over 2 root 3 and up 2. And that's great. That's exactly what we want to define that as. If I wanted to do this in polar form, though, I would need to write it in the format of a radius, right here, and an angle. And the angle's easy because they've already told us what this is. Of course, if you're paying attention to this is a 30, 60, 90 triangle. You're probably already recognizing it is a special triangle that has a multiplier in it. So if I'm realizing that 4 is the radius and the angle is 30. So 4 angle 30. This would be easy for us to do if we were going to do this. And I didn't put this on the board, but let me explain this, why we're going to do this. If I wanted to find out what this angle was, I would say the opposite over the hypotenuse, right, which is the sine, and I would say the sine of theta equals 2 over 4, where the sine of 0.5 is 30, and that's where that number came from. Now, they're giving us this number. They're already putting it in there, but we've done this conversion where we were only given these two, and we find this angle using the sine or using the cosine, depending on our given values, to figure this out, and we could do either one. Now, we're going to employ that same thought process when it comes to the complex plane or the imaginary plane. Here I have 2 root 3 plus 2i. Now, keep in mind, this is from the first part of this lesson, that this is the real plus imaginary number, right? So I have the real number and the imaginary number going vertically. And the real number is 2 root 3, and the imaginary number is 2i. And we were able to get to that very quickly. There it is. It's done, right? Easy. And we can define this point. In rectangular format, that's what it is. However, in imaginary number, in polar form, we run into an issue. This is the combination of real and imaginary numbers, right? That's what that is. This is the combination of the x and the y, right? In fact, if we realize it's a right angle, right, we could use Pythagorean theorem and solve this, and we would have gotten that number. And it works out really well. However, how do you combine a real and imaginary number when they're not like terms? You can't add them up. What are we going to do? So let's go ahead and define that. We know that this is the real direction, this is the imaginary direction, so we're going to say real is going to be dependent upon, this number would be dependent on the cosine, right? Adjacent over hypotenuse. Well, that's easy. What's the adjacent? Cosine of 30 is, for this one, adjacent over hypotenuse. If I wanted to say, well, how could I define just the real direction of 2 root 3? I could say, well, 2 root 3 is equal to 4 cosine theta. That all of a sudden makes a little more sense to me. I can define that. That's how far right that is in correlation. Putting this hypotenuse in the length is 4 cosine of 30, that direction. That's how I would define this using only the real number line. Now, when I define the sine, or the I, the imaginary, I'm going to do the same thing, except I'm going to use opposite over hypotenuse, which is the sine, and that's going to be 2i over 4. 4 sine 30 is going to be equal to 2i. When I start plugging these in, I realize that I could define this right here as the addition of how far right I'm going, how far up I'm going, and therefore I can say 4 cosine of 30 plus I 4 sine of 30, and I'm putting that I in there to tell me that it is on the imaginary direction, right? And when I do so, I realize that this has both 4's in it. So if I factor that 4 out to the front, I'll get 4 times the cosine of 30 plus I sine of 30. Now, this right here is a common form of writing this in polar. Unfortunately, it gets really old writing cosine 30 plus I sine 30 cosine 30, or cosine of theta plus I sine theta, over and over and over. And because a couple of things, this will always be cosine, this will always be sine. This will always be the same angle as this one. It doesn't matter if I'm in second quadrant, it works out that way, third or fourth. It always ends up being these two angles are the same, and it's cosine plus I sine. So like we do everything else in math, when we have something that happens a lot, we come up with an abbreviation for it. The abbreviation for cosine theta plus I sine theta is CIS and the theta. This is cosine I sine. We drop the addition sign out of the middle, and it's not that bad. It's just a matter of an abbreviation. And we realize 4 CIS 30 is 4 cosine plus I sine of 30. And I can break that down as shorthand by going right back to this every single time. And then I could multiply that 4 in and get back to my original formulation of it just as well, and it works out every time. So that's what CIS stands for. You've seen that before, or maybe some of you never understood what it meant, but 4 CIS 30 is the complex graph or complex polar form of a complex number. It's just a polar form of a complex number. So this is not too bad. We will go a lot of conversions back and forth. Notice the conversion here is exactly like the rectangular coordinates. That's why we're not spending a huge amount of time on it. We are converting them exactly the same from rectangular to polar or polar to rectangular. It's just in the real number line up here, we don't have to have that cosine I sine because we can actually figure out what it is. But on this one, because of that I messing me up, I've got to leave it in this format.